Lesson on voltage for honors physics. Conservation of energy. Here we have a box suspended by a string at a certain height above the ground, giving this box some amount of potential energy. I then cut the string and the box accelerates downward, gaining kinetic energy. Here the potential energy of rest due to gravity was transferred into kinetic energy of motion. And the kinetic energy at this location is equal to the potential energy it had at this height, thus conserving energy. Similarly, if we have a positive charge here suspended by a string a distance away from a negative charge, if we cut the string here, we can see that this positive charge will attract to the negative charge and gain kinetic energy. But where did that kinetic energy come from? Well, it also came from a potential energy, but an electric potential energy, or EPE. Here the electric potential energy due to these charges was converted into kinetic energy. Let's take a look at our example from class where we had this negative sphere a distance away from our negative Van de Graaff generator. Here we push the charge closer to the Van de Graaff. Let's observe what happens as we let go. As you can see, it repels away. Let's look at that more closely in slow motion. Let's call this location where the ball is right now point A. At point A, it has some amount of electric potential energy. As we let go, we can see that the ball repels away and gains kinetic energy. Let's denote its new location as point B. So as it moves from point A to point B, its electric potential energy decreases and it gains kinetic energy. Thus, the kinetic energy at point B will be equal to the difference or the change in electric potential energy from A to B. We can also observe, since the Van de Graaff is negatively charged and the ball is also negatively charged, that this charge will move from a place of higher potential energy or higher electric potential energy to a lower electric potential energy. Just as if you dropped a ball, it would accelerate towards the earth and go from a high gravitational potential energy to a lower gravitational potential energy. A Van de Graaff generator like this can be charged up to 100,000 volts, whereas your electric socket can be charged to 110 volts. So why then is it safer to touch the Van de Graaff generator as opposed to the outlet? Well, the answer lies in the concept of voltage. Voltage is defined as the amount of electric potential energy per charge. Where electric potential energy is measured in joules, charge in coulombs, and hence a joule per coulomb is known as a volt. Let's apply this definition and see if we can understand why the Van de Graaff is safer to touch. Let's suppose the Van de Graaff has a voltage of 100,000 volts and the electric outlet has a voltage of 110 volts. Here we can see the Van de Graaff generator at 100,000 volts provides 100,000 joules for every coulomb of charge. The electric outlet supplies 110 joules for every coulomb of charge. And herein lies the difference. 1 coulomb of charge is about 6 times 10 to the 13th electrons. There is no way I can store that many electrons on this Van de Graaff generator, mostly due to its surface area and size. What's more realistic is that I could store about 0.001 coulombs of charge on this Van de Graaff. With that few number of charges, you can see it would only supply with about 100 joules of energy. In contrast, the electric outlet can supply tens of hundreds of charges and rack up a large amount of electric potential energy. So it's not the voltage that does you in, but it's the number of charges. So the Van de Graaff, although it's at a high voltage, has very few charges and is safe to touch. Whereas the electric outlet has a low voltage but has tons of charges flowing that transfer a large amount of energy to you and can be quite dangerous. Let's take a look at our example of the negative charge and negative Van de Graaff generator and relate voltage and electric potential energy. Here I have my negative charge at a certain point. If I do work on this charge and exert a force times the distance that I move the charge, that work will increase the electric potential energy. As I let go, this charge will then accelerate and gain kinetic energy and fly past the starting point. Here we can see the charge now has some final kinetic energy at this location. That kinetic energy was due to the increase in electric potential as we brought it closer to the Van de Graaff. We also noticed that it had some initial voltage here and that voltage decreased with the distance that I got away from the Van de Graaff generator. Thus, if you know the voltage at this location, you could figure out for a given amount of charge how much electric potential energy it would have. And as it accelerates from that high electric potential to a lower electric potential, you could figure out its EPE at this location as well, based on the new voltage, the lower voltage it's experiencing. That kinetic energy then would be the difference of these EPEs, and by knowing that K is 1/2 mv squared, you could solve for the velocity of the charge as it flies by this point. Thank you for watching, and see you in class.